perceptron classification. And so pretty much what it is we have this learning algorithm, which we input a list value of x's, and we get an output, and then we have a desired values of y's for the inputs x. And then we find the distance from our desired value of y by find the distance by taking the desired value minus our output. And then we use this we update what we call the weights, which then input back to give us a new output. So as the output gets closer to our desired value of y, the weights will get smaller, or the change in the weight will get smaller. So over time, the weight will become more constant.
And why would we want the changes to get smaller over time?
So that we can get like a constant value for the weights.
Yeah, so it'll converge, right? You wouldn't want it to keep going.
Wait, do you want the distance from, so you both want the distance from correct y value and the delta w2?
The distance like gives you the delta
Oh, so
w.
you want the distance to get smaller, so the delta w is small, or is the same?
Yeah. You want as the distance gets smaller, like the delta w
Get smaller.
will then increase.
Right.
So then w will like increase or decrease by a smaller amount and like
Right.
essentially remain constant. And then so L is like a learning rate, which is a small fraction, which makes it so delta w doesn't fluctuate too much, and it'll change slower. So yeah, eventually you want it to be so d will be minimized and w will be constant.
Awesome. Do we remember what L is for this lab? Yeah. What'd you say, Jennifer?
Y value.
Exactly. So now we'll use it in a minute. Okay. Ready?
Okay. So we have 3 different like Boolean logical operators, I guess. And so we input these x values, and they're pairs of x values essentially. And for each pair, we want to get a certain output y. So for and, it'll only say, if you say like zeros are false and ones are true, you only get true if you have 2 ones. Otherwise, it will always give you false. And then or, you can either have 2 ones or just 1 of each. But if you just have 0 and 0, it will give you false. And then XOR is the same thing as OR, except if you have 2 ones, it will get false instead of true.
Yeah. So or but not and, right?
And then so for the actual function, we have 2 functions. The driver, which is called pdrive, which it just calls a function we write called perceptron, which is what does the learning algorithm.
Awesome.
And for perceptron, the input values we put are these x's, and for each of the 3 problems, they remain constant, and what we change is our desired y values.
Awesome. And do you see why they remain constant if we go back up here? Because it's the same set of inputs, right? You're just telling it that you want a different output or a different y value for each of these different sets, okay, based on whether it's and or XOR. Good. Here.
And then so, yeah, we input the x's and the y's, and the outputs we get are 2 different weights. And then we'll get different weights depending on what the y value is.
Right.
And then, I'm not really sure what the theta is.
Okay. Yeah, we're gonna spend some time talking about that,
use,
the bias bit. Yeah.
The weights to plot a function, so that you get this line. So that, like, if you have the 0.10, since it's an and problem, it will be red, which represents false. And so anything above the line will be true. So the only point above the line is 1, 1. So that'll be true. And the other graphs will follow like a similar pattern.
Right.
But the only exception is XOR doesn't work because there's no way to plot a line. So like above it, you'll have just greens. Yeah, just the way it's literally inseparable.
Yeah, there's no way to divide the 2D plane such that all points on one side of a straight line will fall into one class, right? And all points on the other side will fall into a different class. You'd have to have something nonlinear. Okay, thank you, Brian. Awesome. Okay, so we're going to go quickly over the learning algorithm. Is that the part on which we're having the most trouble, or is it the bias bit and the plotting? Or all of it? All of it? Okay. Well, then we'll review the learning algorithm, and then you'll need your playing cards because we're going to run a simulation with that, and then we will move into the bias bit and the plotting to wrap up. So Brian gave us an outline of the learning algorithm. I want to take that away and try and derive it really quickly. So you have your perceptron, and in the notes we say that it's a form of supervised learning. What do we think that means? Why would it be supervised as opposed to, say, unsupervised?
You're checking
Go ahead.
the outputs to see if they're working in the direction you want them to.
Right, so you have a direction you want them to, which is what in our case? What do we call it? A vector of desired outputs, y, yeah. So in an unsupervised case, you wouldn't have that, right? And so you'd look at data clustering and different types of patterns, and your learning algorithm or whatever you were training would just have to learn to recognize these patterns in natural scenes or data sets over time. But here, you know what you want the output to be. You want it to be a 1 or a 0 based on the classification problem. And perceptrons are very, very interesting. And when you make them more complicated, which we'll do later in the semester, you can add other layers. And the Postal Service actually uses these guys to recognize all the handwritten addresses on mail. And so anytime you have a known output, any type of character recognition, speech recognition, you can use a perceptron. You know what you want. You train it to respond to that data in a certain way. So you have your Y, and then what's the output of the perceptron? We're calling that O, right? So we want to compare O to Y. Before we do that, though, we have to calculate what O is. How do we do that? Brian just had it up there. Hopefully you remember it from the notes. What would O be in this case? The sum of what?
Is it like x1, w1 plus x2?
Yeah, x1, w1, x2, w2, x3, w3. So it's a weighted sum of the inputs, and it's weighted by w1, w2, and w3. So we can write that as OJ sum over all neurons of the weight times xi. And what's xi? A 1 or a 0, okay. So it's the input to that neuron, 1, 2, or 3, okay? So on the jth iteration, we're going to give neurons 1, 2, 3 inputs xi, x1, x2, x3. Multiply them by the weights and calculate the output. There's one more thing here, though. The output needs to be binary, okay? And later we'll extend this problem to non-binary inputs. So what do we have to do with this weighted sum before we move on? Okay, how do we do that? Go ahead.
There's a function that takes the sum and returns a 1 if that number is greater than 0 or 0 is less than or equal to 0.
Exactly. All right, so we pass it through such a thresholding function, f of that quantity. For ease of notation, we can call that quantity theta for now, all right? So if that weighted sum of inputs is non-negative, so if theta is greater than or equal to 0, f of theta equals what? 1. What if theta is less than 0? What's f of theta? 0. All right, so now our output has become either a 1 or a 0, okay? Because this may not always be 1 or 0 if our learning rate's really small, right? If it's 0.01, we're not going to necessarily have sums that are 1s and 0s. Okay, so now we have this output. Are we clear on how we got there? Yeah, Jennifer?
So the function is just like the thing above there, or like,
The thresholding function?
so the function is just 1 or 0?
Yeah. Yeah, how would we set that up in our code?
Like an if statement?
An if statement, exactly. How would it work? If what?
If,
Let's call this some theta, or whatever you want to call it.
is it just like if theta is 1, or
What's our first case?
I is 1,
Does it have to be 1?
or
This is theta, so the quantity, that sum, we're calling theta. Okay?
oh, so if theta is greater than 0, then like f of theta is 1.
Exactly.
Is that like percent?
The f is just, it's a thresholding function, okay? You don't even have to, you're not going to have to write f in code. The if statement just, it takes care of it, right? So if that theta is greater than 0, you're going to calculate this before, okay? W times x. If that product is greater than 0, then OJ,
Oh, then OJ.
right, exactly. Then it's 1, and otherwise OJ is what? What's OJ otherwise? 0, exactly. All right, so now that we have this OJ, what's next? What do we do with it?
Compare it to y.
Compare it to y. So we look at y minus OJ. Does y change as we keep doing this over time? No. Y is our desired output. That's not going to change. And we call this D, is the difference between what the perceptron outputs and what we want it to output every time. And I think on the quiz there was a question about possible values of D. What could D be in this case? What'd you say, Rachel? 1, 0, negative 1, because our OJ is restricted to 1 or 0 because of f of theta, right? And y is either going to be 1, 0. So the only things you're going to have in this simple case are 1, 0, negative 1 for D. Once we have that D, we do one last thing. What do we do with D? Yeah, we find delta W, and what is delta W? Next.
How you're going to change the weights.
Yeah, it's the change in each weight. So each of these guys has its own delta W, okay? Because we're governing how this thing evolves over time in the distribution of these weights, so it solves the problem in the way that we want it to. So what is delta Wi for each weight?
Lowering rate times the input times the difference.
All right. So our learning rate, like we said, is 0.01, and that's what we're going to use in this problem at least. And we're keeping that small y. Brian mentioned it in his presentation.
You don't overshoot your target value.
Yeah, exactly. You don't want to overshoot it, because if you get a set of inputs, say in the real world, that was a bit off, and you made a huge change because of that, then it's going to take tons of iterations just to recover. And so you want to keep your jumps small so you won't overshoot the set of weights that you want to converge onto. All right, so xi is your input, which you already have, and d is your difference, which you just calculated. And that's it. So you calculate your delta Wi, and then how do you update the weights? What would you do there? New weight equals what?
Old weight plus delta W.
Exactly. So if there's room here, we'll do W plus equals W plus delta W. But that needs to happen for every single neuron. How could we keep track of all these at once? We don't want to do a for loop and cycle through every neuron. It could be really big. You could have hundreds of these guys. We're not. We're only working with 2. But just, hypothetically, if you had a lot of input neurons, how would you do them all at once?
Iteration.
Okay, so in one iteration, do you want to do for I equals 1 to number of neurons, each neuron equals old weight plus new weight? How else could we do it and just add them all at once? Yeah, Max?
Matrices.
Yeah, matrices and vectors, okay? You just represent the weights in a single weight vector, okay? And when you update it, you would just add the vector to the delta W vector. Okay, so Jennifer?
So, why do we have, so we have 3 weights, Why are there 3? Is it
Why are they there? This,
or is it like all for 1?
this is just, I'm sorry, that wasn't clear. This is just an example. So you could have, theoretically, you could have n of these guys.
Yeah.
This, I just drew it that way because you're about to get into groups of 3. So it could be, it's theoretically Wn, right? You can have n of these guys. In your example, you're only going to have 2, right? Because if we remember, oh, there's a caveat to that. We'll have to add an extra one for another reason, but don't worry about that yet. But you're just going to have x1 and x2, okay? So this is just an example. All right. Any other questions before we move on? No? Yeah.
How do you make a vector? Or like, how do you make, like, if you wanted y to just be like an empty vector, but, or like, I don't know.
To initialize a vector without anything in it?
Or yeah. Or I don't know.
You could do that here. Does anybody know? How to initialize a vector without anything in it, just allot the space.
Do y equals and then open and close the
What kind of brackets?
square one.
Yeah, exactly.
Like, if you wanted it to be a certain size or something, you have to do that, or will you just define that later?
This guy won't have a size. How could you initialize it to be a certain size? Zeros. Yeah, I don't know if you've done that yet. Some of you may have in the Newton routines. But yeah, if we wanted to make it say 1 by 4 and initialize it to be that size, what would we do?
Y equals 0, 6, 1, 4.
Yep. So that's going to give you.
Size going forward?
Nope. That's just going to fill you with zeros in those dimensions. I mean, it's going to be 1 row and 4 columns, so it's a row vector. But if you don't fill all of those entries with whatever you want, they're going to be a 0. And so you need to remember that they have zeros in those places. All right, are we good?
Are those just being
Yep.
brackets?
Nope, zeros is a built-in function in MATLAB, so you can just fill a matrix with zeros, vector with zeros, whatever. Anything else? No? Okay, look at your card for me. And we should have, we've got 1 person absent. And so I need you to move in groups of 3 based on your suit. So whose hearts? Okay, you guys will be a group of 2. You're going to be special. We'll talk about you in a minute. So clubs. Do we know what clubs are?
Yeah.
Yeah, okay, so clubs. No? Do we know what clubs are?
Yeah.
Okay, then clubs need to sit together. Yeah, somebody behind you may not have. Diamonds, who's diamonds? Okay, you guys need to sit together. And what do we have left? Spades. You guys need to sit together. So get in your suits. No computers, but you'll need a piece of paper and a pencil. Okay. Do we have 2 groups of 2? Is that how it worked out? Okay, you guys have a choice. 1 person, we're going to have 3 input neurons, right? And you're each going to get an input. And so for the 2 groups of 2, one of those people can either be 2 input neurons, or you guys could become a group of 4. And you could have 2 people on 1 input. What would you like to do? What do we think? Stay in groups 2? Yeah? Okay. So what we're doing is your jacks are going to be, if you have a jack, and this is just for the groups of 3, jacks are input neuron 1, queens are input neuron 2, and kings are x3. Okay? And at each iteration, we're going to give you a round of inputs. Okay, so input neuron 1 in this example would get a 1, 2 would get, or your queen would get a 0, and your king would get another 0. So the groups of 2, what do you two have?
King.
You've got a king, you've got a queen. Who wants to take jack? Okay, what about in the back? What do you have?
Jack and queen.
Who wants to take king? Awesome, thank you. Okay, so at each iteration, I'm going to give you your inputs, and we're going to do 5 of these, all right? I'm going to give you your inputs, and based on the learning algorithm, which I can rewrite on the side if we need it, you need to calculate as a group your output, okay? So once you're done calculating your output, hold up either a 1 or a 0. We have this here. Would you guys pass this down to him? Okay, so what does that mean? Each person is going to have to calculate their contribution, right? So x1 times w1 for the jacks for neuron 1. For neuron 2, you would do x2 times w2. And then as a group, you need to sum those outputs and then do what with them? Yeah, decide if it's 1 or 0, so pass it through that thresholding function. So what do you individually need to keep track of over time? What's going to change? Somebody said it. The weight, exactly. So you need to keep track of your weight on your paper based on these inputs, and I want everybody's weight to start at 0. Okay? Do we know the learning algorithm well enough? Can you talk about it amongst yourselves, or do I need to rewrite it on the side where you can see? What do we think? You got it?
The starting weight is 0 and the sum is 0.
Exactly. So the starting weight's 0. Are we good on what we need to do? All right, so let's try round 1. Here are your inputs, 1, 0, 0. Everybody calculate the output of their perceptron, and then you need to update your weights before I give you the next one, okay? Okay. You guys got it?
What would our Y value be though?
Well, okay, we're performing the OR task. You also need that information. So if you have these inputs and you're doing an OR task, then what do you want your output to be? 1. So what is your output if all the weights are initially 0? 0. So your D is 1 minus 0, right? So your D is 1.
So for each time, do we say y is 1?
Well, it depends on the inputs, right? If we're performing the OR task, when would y not be 1? If it was 0, 0, 0, right? Or is if anybody's on. So if nobody's on, then y 0. Yeah. Y is what?
The output 0?
The output 0? Well, all your weights are 0, right?
But isn't on that function,
Mhm.
it's non-negative, isn't it 1? So.
Good catch. Good catch. Then we may need to... I wrote it wrong. Greater than 0. Sorry. Good. Yeah, very good call. When you're done for this one on the output of your actual perceptron, not the desired, you need to raise your card so I know you're done. Are we good? So what was the output this time? 0, right? Because the weighted sum of the inputs, all the weights are 0. So 0 times whatever the inputs is. OJ is 0, okay? Then you pass it through thresholding function like we just recognized, like Jack said. That was a little bit off. But then the difference, then what do? Somebody needs to update their weights, okay? Which neuron needs to update? The first one. Why? Yeah, it's the only one who's going to get anything out of this, because if your input is 0, can you change? No, why not? Exactly. So the perceptron accounts for updating itself and learning and evolving, right, based on whether or not those neurons actually get anything inputted to them on that iteration. So what does your neuron 1 need to do at this iteration? What's it going to become next time? What's its new weight? 0.01, right? Because L 0.01, DJ, what's DJ for input neuron 1? 1, right? So this is going to be the same for everybody. D is the same, because there's only one output and there's only one desired output. But whether or not your individual weights change based on that D is a factor of whether or not they got anything, right? Whether they got an input. Okay, so now input neuron 1 is going to have a positive weight. It's going to be a connection there, right? So next round of inputs. The other two weights are still what? Still 0, okay? Now your jacks, now your input neuron 1s have a weight of 0.01. So second round of inputs, neuron 3 gets an input and neuron 1 does not. What's Y? What's our desired output here? 1, right? It's an OR task and one neuron got an input. So calculate the actual output and then raise your card when you've got it.
Can you write the F of theta over there?
What was f of theta? Do y'all remember? 1 if theta is strictly greater than 0, we've decided, and 0 if theta is less than or equal to 0. Okay? So first thing you need to do is calculate theta. And what's theta? The weighted sum of the inputs. What are the inputs? These guys. What are the weights? 0.0100. So what's theta in this case? 0, right? Because weight 1 is the only existing weight, but there's no input there. So the weighted sum of the inputs is 0. What's f of theta? What's OJ? 0. So everybody should be holding up a 0. Awesome. All right, then what? Then what do we have to calculate? The D. What's D here? 1, because your desired output is 1 since it's an OR task. So D is 1. What's delta WI for the first neuron? 0, because Xi is 0. What's delta WI for the second neuron? 0. What's delta WI for the third neuron? 0.01. Why? Because our learning rate's 0.01. We just said D is 1, and X3 is 1. So now neuron 3 needs to add what? 0.01 to the existing weight of 0. Okay. Ready for the next one? So work through those same steps on your own, okay? And raise your card when you've got the existing output. What do we want it to say in this case? Okay. But what does it actually say? Why do we want it to say, why do we want it to say 0? It's an OR task, right? What does an OR task mean? We're following these tables, okay? So in an OR task, if everybody, so here we have 3 input neurons, but it's the same principle. In an OR task, for the output to be desired to be 1, you have to give an input to one of the neurons or the other, or all of them, right? And the only case in which we want the output to be 0 is if nobody receives an input at all. If this were an AND task, alternatively, and we gave, well, that doesn't really help. What about if we look up at example 2? If this were an AND task, what would the desired output be? 0, right? So you can look at the same set of inputs. I mean, we're giving the perceptron function you're going to write, the same set of inputs, but the desired output changes based on the classification task. Okay, so the desired output here was 0. And what's the actual output? 0. So is anybody going to change? No. So neuron 2 still does not have a weight. Next one. So before you even do D, you need to find the current output of the perceptron, right? You need to do OJ. What's OJ? 0.01? Right. So but this perceptron only has binary outputs, right? It's either a 1 or a 0. So it's a 1. Why is it a 1, Rachel? Yeah, you have to pass this weighted sum. The weighted sum is 0.01, right? But you have to pass that through your thresholding function to make sure your output's binary. No, just if, we just made a change in the signs a little bit, but that's it. So the output at this iteration is 1. Everybody got 1? Okay. So who's going to update? No one. Why? Yeah. The desired output is 1, and your actual output you just said was 1. So DJ is 0. So nobody's going to update. So because neuron 1 has a weight, you're preventing neuron 2 from getting anything because your output's already what it needs to be. But this would fail. What would happen right now in this weight distribution if we gave an input to neuron 2? What would the output be? That's actually our next one. First answer the question, what's the output if in this scenario with the weights you have, if we give an input only to neuron 2? Raise your thing when you got it. Why is it 0?
Because the weight of that one is.
Yeah, because weight 2 is 0. So it doesn't matter that we're giving it something it can't communicate with the output neuron because there's no weight between them. Okay, so what's our desired input, or our desired output? 1, right? Because it's an OR task and somebody's getting an input. So now we have a DJ, which is, somebody said it. It's 1, yeah, right? Because our output we just said is 0, desired is 1. So that means we get to update. Who are we updating? Yeah, the queen, neuron 2, right? So what's our update going to be? 0.01. So we see that the OR case is unique, and well, it's special because what are the weights that we're going to converge on? What are they going to be always? Not, well, 0.01, not just because that's the learning rate, but the perceptron will stop learning once everybody has the same weight, right? Once everybody has a weight. The fact that it's the same is just kind of an artifact of our algorithm, right? But now, since they all have 0.01, if we give one input to any of these neurons, since it's an OR task, since these weights are all positive, it's going to return something, right? It's going to return something greater than 0. And that's enough, once you pass it through the thresholding function, to give us a 1, right? And an input to any of these neurons in the OR task, the desired output's a 1. So that 1 and that 1 cancel each other out. You have no D. And so you've converged on an optimal set of weights as long as everybody has some type of contribution. Do we see that? Yeah, okay. So we need to move on and get to the bias bit and then the plotting in the rest of our time. And to motivate that, we have the question of what if we handed this guy something that wasn't binary, right? Right now we were looking at giving it a 1 or a 0, but what if we gave it a 0.5 and a 0.9? What would it do, right? So that's why we're writing the rest of the code. That's why we're giving it to the driver and doing the plotting to answer that question. Because in real life, you're not going to give it 1s and 0s, right? If it's recognizing characters, you're going to give it a matrix of values that represent luminosity, curvature, anything, right? So it's not always binary. Brian went over this outline already, so I don't want to dwell too much on it, but you've got your driver and your perceptron function. Do we remember what those are each responsible for? What does your perceptron function do? The learning part. It executes the learning algorithm and returns, generally, the weights, the optimal set of weights. Yeah.
So is WO or delta W?
WO is something special we're going to talk about in a minute. It's the bias weight.
So we should set.
Yeah, don't worry about WO yet. We'll talk about that in a minute. But perceptron takes as inputs these X and Y's, which we'll talk about, and returns the optimal weights. What does P-drive do? Plots them and has to call it, right? How many times is it going to call perceptron? 3. Why 3? 3 cases. These 3 cases, okay? So we just said that. It calls it 3 times, and it's going to plot. Then the perceptron needs to carry out the learning algorithm, right, and then return the optimal set of weights. So our input structure, what are we giving perceptron? What is this X and Y, right? It just follows directly from the tables. X, as we've been saying the whole time, is going to remain consistent across all 3 trials. We're just saying that based on this one set of inputs, we're going to have different desired outputs corresponding to the task, okay, or and or XOR. So what form would these take? How would we pass X and Y to perceptron? What's X going to be? A matrix, okay, with how many rows? 4. And columns? 2. What's Y going to be? A column vector, right. And we hard code these in the driver, all right? You don't have to use combinatorics or anything and come up with them. You just say X equals 1, 1, 0, 1, 1, 0, 1, 1, or 0, 0, whatever, right? And then you're going to code, hard code, a different y every time you call perceptron for the 3 different problems. Okay? So before we move on, I say you need to do this in the notes, Jmax times. What does that mean? Do we remember what Jmax was? 1,000. What was Jmax in the simulation we just ran? How many times did y'all do it? 5. So Jmax is the number of times we're handing a set of inputs to the perceptron to train it. In our case, however, we have these 4 different inputs, and you need to pass each of them, each pair, right? One set of inputs would be 1, 1, 1, 0, 0, 1, or 0, 0. You need to pass each pair to the perceptron to train it 1,000 times. So 30 seconds in your groups, talk about how you would embed that for loop structure, okay? 30 seconds, go. Okay, Emily, what did your group say?
Still discussing.
Okay, anybody else want to share? Do you have something?
If you did run through the perceptron 1,000 times
Okay, so how would we set that up?
for Jmax.
For, well, let's call it J, right? 1 through what? Do we know it's 1,000? Yeah. So we need to set Jmax within perceptron, right? It's not an input. Then what are we going to do? Can you pass the entire matrix through at one time based on the way we have it set up? Could. What would be an easier way to do it? Yeah, line by line. So within there, you could have another kind of loop. What could you put? A for loop. For what? Not, well, don't reuse J. We already got J up there. Okay? To what? 1 to, awesome, length x. Yeah, make it arbitrary so it could accommodate an arbitrary different number of inputs, even though we're only using 4. So 1 through length x, because x is already going to be specified. Then execute your algorithm, okay? I can trust that the execution it's not that bad, I promise, if you just directly code the steps we talked about and the steps in the notes. Okay, so perceptron needs to return this W and W0. So the last thing we need to address is the same question, handing it the non-binary inputs, but from this discussion we recover this bias bit, okay, or that W0, that's the other output of perceptron. So to see this, what we've been doing is we've been summing the inputs, all right, and that's theta, before we pass it to the thresholding function. Are we good there? That's the weighted sum of inputs. We can rewrite this as the equation for this line, okay? So we just move theta to the other side. What would that line represent? Everything on one side of this line. If that's the line where the weighted sum of the inputs compared to theta is 0, then everything on the one side of the line is going to be everything the thresholding function would return as a 1. And everything on the other side of the line would be what the thresholding function would return as a 0. Does that make sense? That's like the dividing line for this plane based on what the thresholding function would return for a given input. That input doesn't have to be binary. This is a line dividing the plane. Do we see how we got it? Yeah? Okay, so that's this line. Here's our OR case. That's a simple line. Everything on this side, as long as somebody's getting an input, a non-zero input, then the perceptron's going to return a 1. So we need to calculate theta. Okay, we don't have that. Theta is just the weighted sum of the inputs. And we move that over to the other side and we say, okay, so we have our optimal set of weights, but how do we choose theta? And the answer, and this is given in the notes to make things a bit less complex, but this theta we pretend, well, we call it W0, same thing, right? And we pretend that there's an x3 there, right? Because that theta is always going to have a coefficient of 1. So the way we can account for that is adding an x3 or an input neuron that always has an input value of 1. Okay? So if we let that x3 be 1, then we have the equation of the line. And the trick is that if you give the perceptron one more input at every iteration, and that input is always 1, then it'll automatically calculate that W0 for you. You're just pretending that you have one other input neuron whose input is always 1. It's always given a 1 every time. Okay? And then the weight for that neuron on the end is your bias weight, and that's the weight you're going to return as W0. So if you're adding an extra input neuron to the perceptron whose input is always 1, we need to update what that we pass to perceptron? Our X matrix, exactly. This has only 2 input neurons, right? So how can we update that to include an input neuron whose input's always 1? Add another column, right. So that column would be a column of 1s. So you have your existing X matrix, you augment it by adding another column of 1s, and then you pass that to perceptron. So perceptron is going to take that and return a W matrix, right? So the matrix corresponding to all the optimal weights. And it's going to be, well, it's going to be a row vector, and if you've given it 3 different inputs, how many elements is W going to have in it? 3. Do we want 3? Well, we do, right? But we want one of them as W0. So we need to strip that one off, okay? Because the last weight in your W vector is going to correspond to that third column of inputs in X that were always 1, right? So if you have, well, that's a mess, W equals something, your optimal weight vector, okay, then how do we get rid of the last one? Well, we don't want to get rid of it. We want to return it as W0. So how do we strip it off? Tip of the tongue. Yeah, this guy is W0. The third element of the W vector is W0. How can we assign it? W3 what? W0 equals that, right? And then you need to get rid of W3. So how can we get rid of W3? Yeah, W equals W1 to 2, or Wn, the last element of W, is empty. So you strip it off, okay? But don't strip it off, don't kill it until you've assigned it to W0, because you need to return W0. So the very last thing, and then you can go, is how to plot this line, okay? You have your bias bit, you have your optimal weight set, and you need to plot the line W1, X1, W2, X2. You know X1 and X2, you know W1 and W2, and you know theta. What's theta? W0, right, what we just solved for and accommodated in the perceptron. So we need to plot this line on the plane, and you need to scatter the points in each of the 3 cases. There's a handy scatter function in MATLAB that's described in the notes. I trust you can figure that one out. It's not very difficult. So last thing we're talking about, how do we plot this line? We know W. X1 and X2, what are X1 and X2? They're potential inputs, right? They're anything on this line and anything on that line. Because we want to answer the question, what would this thing return for any potential input on the plane, not necessarily a 1 and a 0 like we were running in our sim, right? So what is x1 if we're trying to plot a line? 0 or 0.5 or 1 or 0.8 or 0.2. It's the whole x-axis. Because we want to know what we're going to get out of the perceptron for, say, the 0.7, 0.8. So your x1, to plot a line, you need to pass the plot function of vector of all those points. Okay? What's x2? Yeah, x2 is this guy, but if we're plotting a line, we need to plot it as a function of x1, right? We need to know for whatever input on the x-axis, what's the perceptron going to give us, right? What is that thresholding line for the thresholding function? So if we gave the perceptron an input of 0.1, then what's it going to return? We need to be able to follow it up to the line, right? So the x2 value corresponding to a particular x1 value. How could we get that from this equation? You got it. Speak up. Yeah, move x2 to the other side of the equation. What else do we need to move over there? Theta. And kill w1. We want to solve for x2 in terms of x1. Or, sorry, we want to move w1, x1 over there and move theta over there. Solve for x2 in terms of x1. So what's that going to look like? Right? Yeah, so if you have a vector of points, x1, and x2 is your desired or your corresponding output for that vector of input points, then that's the line you want to plot. Okay? Yeah, Jennifer.
Like, how do you
How do you what?
is W just like initially a vector of 1, 1? And then how do you do W with 3?
What are you talking about?
Like our weight?
Where do the weights come from? Where do we get W? Yeah, that's the output of perceptron. Yeah, what do we want to initialize it at? 1. At 1. I say that in the notes, okay? So you're going to hand perceptron initial weights of W. You update them at every iteration. W equals W plus delta W. And then you're going to return the optimal set.
But do you return them as a vector?
Uh-huh.
How do you do a vector if you have it just equal 1 initially?
Well, every element in the vector is going to equal 1 initially, right?
Is it a vector 2 or 3?
It's going to be a vector 3 because we have that extra input neuron. And then we're going to strip off the last element of W and assign it to W0. Okay? Title it with num to string. Okay? Look at the help function for that. Lin space will give you a nice range of values between 0 and 1.5 for your x1 and x2. Okay? Free to go if you have another class. If you want to stay and ask me any questions or other lingering things, then I'll be here.